They believe it is solid. Not solid in a qualified way, not solid with fine print attached, but solid the way the word solid was invented to mean. The kind of solid where you can set a glass down and walk away, and it will be there when you come back. The kind of solid where the floor holds your weight, because floors hold weight, and that is simply what floors do. And they are right. But here is what they were never told. That solidity, the realest and most reliable thing you will ever press your feet against, is an illusion built on emptiness. Not emptiness in the poetic sense, not a metaphor or a philosophical observation about the nature of things. Emptiness in the literal sense. The atoms that compose the floor are almost entirely empty space. The nucleus of a hydrogen atom, the positive core at the center of the simplest atom in the universe, is 100,000 times smaller than the atom itself. Scale a hydrogen atom to the size of a football stadium, and the nucleus would be a grain of sand at the center of the field. Everything else, the entire vast interior of the atom, is nothing. The floor is solid. The glass stays. The weight is held. But here is what they were never told. That solidity, the realest and most reliable thing you will ever press your feet against, is an illusion built on emptiness. Not emptiness in the poetic sense, not a metaphor or a philosophical observation about the nature of things. Emptiness in the literal sense. The atoms that compose the floor are almost entirely empty space. The nucleus of a hydrogen atom, the positive core at the center of the simplest atom in the universe, is 100,000 times smaller than the atom itself. Scale a hydrogen atom to the size of a football stadium, and the nucleus would be a grain of sand at the center of the field. Everything else, the entire vast interior of the atom, is nothing. The floor holds you up not because it is there. It holds you up because quantum mechanics will not permit it to let you through. Get comfortable. Hit subscribe if you are new here, because by the end of this, everything that feels most solid in your world will have changed its meaning, and the floor under your feet, the same floor, not moved, not altered, will be telling you something entirely different, the brick you cannot find. Now let us ease in slowly. Human beings have been asking what things are made of for as long as there have been human beings to ask. The ancient Greeks had a word for it. Atomos, the uncuttable thing, the irreducible piece, the thing you could not subdivide further because once you reached it, you had found the bottom, the smallest possible something, the last piece of the world. It is a beautiful idea, and for a very long time it seemed to describe something real. As chemistry matured in the 19th century, the atomic picture became increasingly hard to resist. Elements combined in specific ratios that only made sense if there were discrete building blocks being assembled and reassembled. By the late 1800s, the atom was no longer a philosophical proposition. It was a working assumption that made chemistry work. The periodic table organized the elements in patterns that implied internal structure. The atoms were real. The question was what was inside them. But here is where the story turns strange. Not just more complicated, not just more detailed, genuinely, fundamentally strange. Because when physicists went looking for what electrons actually were, they discovered that the question, "What is it?" may have been the wrong question from the start. The first answer came in 1897, when J.J. Thomson in Cambridge measured the mass and charge of a particle that emerged from every material he tested, regardless of what it was made of. This particle, The electron was universal. Every substance in the universe seemed to contain them, and the electron was roughly 2,000 times lighter than the lightest atom. So atoms contained something smaller. The era of the uncuttable thing was already over. You have probably sat near a candle flame and watched it flicker. The flame seems to be a thing. It has a shape, a color, a location in space. You point at it and say, "That flame is here." But the flame is not a thing in the way a stone is a thing. A flame is a process. It is burning, happening. The material that makes it up is constantly different material. The flame itself is not a collection of fixed stuff, but a pattern of activity that maintains its form, while its substance flows through it and away. The photograph that could not be taken. By the early 1900s, physicists had accumulated a stack of experimental results about atoms and electrons that were, taken individually, fascinating, and taken together, completely incoherent. They showed things that were impossible if electrons were tiny, solid spheres following predictable paths around atomic nuclei. They showed things that were impossible if electrons were spread out waves. They showed, in fact, things that seemed to be impossible under any consistent physical picture anyone could imagine. This is not a story about electrons being shy. It is a story about something far deeper. The act of looking, of measuring, of gathering information about the electron's path fundamentally altered what the electron was doing. Measurement was not neutral. The observer was not separate from the observed. The very attempt to know which slit the electron passed through prevented the electron from passing through both, which is what it does when no one checks. Electrons, when fired at a thin barrier with two small slits, would create interference patterns on the wall behind, the unmistakable signature of a wave spreading through both openings simultaneously and canceling or reinforcing itself. But when you tried to catch an individual electron doing this, when you tried to detect which slit it had actually gone through, the interference pattern vanished. The electron behaved as a particle the moment you looked at it. It refused to be a wave while you were watching. One equation, one island, one dawn. That is not a feature of our ignorance. It is a feature of the universe. He had brought his mathematics with him. Heisenberg asked his supervisor for 2 weeks of leave and escaped to an island in the North Sea called Helgoland, a small, treeless, rocky place scoured by wind, far enough from the mainland that his hay fever retreated. The cold air was clean, and the sky was large, and there was almost nothing there. A place as close to empty as a populated place on Earth can be. Let us go and sit beside him in that absence, because this is the kind of moment that deserves to be inhabited rather than just described. He is alone. The hay fever is lifting, and the fog of it is lifting with it. He has been sleeping badly and thinking constantly, and now on this sparse island with no pollen and no city and no colleagues to talk to, his mind is finally clear. He walks. He reads Goethe poetry at night, the way some people do mathematics when they need to rest from poetry. And in the gaps, he returns to the problem. The insight that came to him there was almost philosophical. He had been trying to calculate the precise path of an electron inside an atom, the arc it traces as it orbits. He had been treating the electron like a tiny planet on a small circuit, trying to derive its exact trajectory. And then he stopped and asked himself a question that seems almost too simple to matter. Has anyone ever seen that path? Has anyone ever actually observed an electron moving along an orbit inside an atom? Heisenberg decided to build his physics only out of quantities that could actually be observed. He stripped away the orbit, the unverifiable picture, the comfortable image of a particle on a tiny track, and worked only with what the experiments could measure. When he did this, the mathematics finally yielded. A framework emerged that he barely recognized, a set of tables of numbers that obeyed strange multiplication rules, rules where the order of multiplication mattered, where doing A then B gave a different result than doing B then A. And the honest answer was no. No one had. What experiments showed was the light an atom emitted, the specific colors of it, the precise energies, the gaps between states. The orbit itself was invisible. It was an assumption, a borrowed picture from a world of stones and planets, imported into a domain where it might have no business being. Let us be with him as the light arrives. The horizon line is a hard, dark edge, and then it softens, and then the first flat gold light comes over it and spreads low across the water. The sea is cold, and the rock is cold, and Heisenberg is 23 years old, and he has just written down, he believes, something true. Not approximately true. Not true as an approximation to something better. True, and it is strange. The mathematics is strange. The rules it operates by violate the most basic assumption of classical physics, the assumption that if you measure position and then momentum, you get the same answer as if you measure momentum and then position. In this new mathematics, those two measurements do not commute. You cannot do them in either order and expect agreement. The physical world at the level of atoms does not commute. The uncertainty that builds the universe. 2 years after Helgoland, staring at the strange, non-commuting mathematics he had found, Heisenberg noticed something inside the equations that he had not put there deliberately. It had emerged from the structure of the mathematics itself, the way a shape can be hidden in a drawing, until suddenly you see it and cannot understand how you missed it before. He noticed that the inability to measure position and momentum in either order and get the same answer meant something specific and physical. It meant there was a fundamental limit on how precisely both quantities could be known simultaneously, not a limit imposed by clumsy instruments or insufficient care, a limit written into the structure of reality itself. This is the Heisenberg uncertainty principle, and it sounds at first like a statement about the smallness of electrons, a fact about a regime so tiny that it has nothing to do with the large and ordinary world. But follow it one step further, because there is another version of the same trade-off, and this one reaches all the way from the smallest scales to the scale of the entire cosmos. And this loophole, this tiny crack in the most fundamental accounting rule we know, is not a minor footnote in physics. It is everywhere. It is happening right now. In the space between your hand and the nearest surface, in the space inside your cells, in the space between the atoms of the floor you are sitting on. Virtual particles are flickering into being and vanishing billions of times per second in every cubic inch of what we casually call empty space. The vacuum is not empty. The vacuum has never been empty. The vacuum hums. What the empty cup is full of. Every culture has a version of this object. The empty vessel. The hollow thing that demonstrates the concept of absence by being itself absent of content. The cup is our best everyday example of nothing. We fill it to make it something. We empty it, and it becomes the container of the concept we are trying to think about. This cup is going to be our guide through the rest of this video. We are going to return to it at several points, and each time we return to it, what it is sitting in, the apparent nothingness between its walls and the air around it, is going to mean something slightly different than it did before. Right now, in this first pass, the cup represents what most people mean when they say nothing, a region from which the contents have been removed, an emptiness that is real and uncomplicated, the way an empty fridge is empty, or an empty parking lot is empty. And now, ask what is inside the cup. Now, take that cup and imagine evacuating it. Not just pouring out the coffee, but pumping out every molecule of gas, every atom of air, every photon of light, making it as nearly as possible a perfect vacuum. The kind of vacuum engineers in laboratories work very hard to produce. The easy answer is nothing. That is the point of a vacuum. Nothing is what a vacuum is made of. The quantum mechanical answer is almost nothing. But almost is doing an enormous amount of work in that sentence. Because the Heisenberg uncertainty principle applies to the vacuum just as it applies to everything else. The vacuum has an energy, and that energy, over short timescales, is not fixed. It fluctuates. Pairs of virtual particles are constantly appearing inside the evacuated cup, existing for intervals too brief for any instrument to directly capture, and then annihilating back into the vacuum they came from. This is not speculation. This is not a theoretical possibility that might or might not be the case. It is measured. There is an experiment, simple in concept and precise in execution, that confirms it directly. Place two metal plates very close together in a vacuum. They should feel no force, because there is nothing pushing them apart or pulling them together. But they do. The quantum vacuum exerts a pressure on the region between the plates, a pressure that differs from the pressure outside, because the geometry of the plates excludes certain wavelengths of virtual photon from the space between them. The result is a tiny but measurable attractive force. The empty cup is not empty. It is full of the quantum foam of virtual particles, the restless jitter of a vacuum that the uncertainty principle will not permit to be still. Every cubic centimeter of the most perfect vacuum that has ever been produced in any laboratory anywhere on Earth is, at every moment, boiling with this invisible activity. Sit with the cup for a moment. It has not moved. It is still on the table. Everything about it that you could see or touch or measure with ordinary instruments has not changed at all. And yet, the thing you thought you were describing, when you looked at its interior and said nothing, has just become something very different. The sun's debt to the unknown. In the middle of the 19th century, the brilliant physicist William Thomson, known as Lord Kelvin, turned his considerable intelligence to the question of how old the sun could be. He approached it as an engineering problem. The sun is an enormous mass of gas. That gas is compressed by its own gravity to high temperatures. Hot gas radiates energy. How long before the fuel runs out? Kelvin was not wrong about the physics he knew. He was simply missing a source of energy that no one in 1862 knew existed. Kelvin's answer was roughly 20 to 40 million years. A long time in human terms. Not nearly long enough for the Earth's geological record, which by that point was already suggesting an Earth of hundreds of millions of years. Certainly not long enough for Charles Darwin's newly proposed evolutionary processes, which required vast spans of time to work. The source turned out to be sitting inside the nucleus of every atom in the sun's core. When hydrogen nuclei, protons, fuse together to form helium, a tiny fraction of their combined mass is converted directly into energy according to Einstein's famous relation. The energy released per fusion reaction is small, but the sun contains an unimaginable number of protons, and the reactions proceed continuously. The total energy output is enough to power the sun for 10 billion years. This was understood by the 1930s, but it immediately produced a new problem, one that was in some ways more troubling than the old one. This was understood by the 1930s, but it immediately produced a new problem, one that was in some ways more troubling than the old one. For protons to fuse, they have to get close enough together for the strong nuclear force to grab them. The strong force is very short range. It operates only across distances comparable to the size of a nucleus. At any greater distance, it does nothing. So two protons have to come within a nuclear diameter of each other. And yet the sun burns. The sky is bright. The calculation is wrong somewhere. The place it is wrong is in the assumption that protons are particles with definite positions. They are not. They are quantum objects described by wave functions. A wave function does not end abruptly at the edge of a classically forbidden region. It leaks through. A proton approaching the repulsive barrier of another proton has a wave function that extends with exponentially decreasing probability through the barrier and out the other side. There is a real, calculable probability that a proton will be found on the far side of the barrier, even though, classically, it could not have gotten there. Not because the sun is hot enough to smash protons together by force. The sun is not hot enough for that. The sun burns because quantum mechanics gives protons the ability to slip through barriers they could never climb over. The sun's fire is lit by the uncertainty principle, the same principle that fills the vacuum with virtual particles, the same restlessness of the quantum world that will not let position and energy and all the associated quantities be perfectly pinned down. This is quantum tunneling, and it is the reason the sun shines. And now that we know the foundation, we can ask the largest question the foundation has to offer: the seeds of structure. By the early 1980s, cosmologists faced a puzzle about the large-scale structure of the universe. Everywhere they looked at the largest scales, the universe was remarkably smooth. The temperature of the cosmic microwave background, the faint afterglow of the early universe, was the same in every direction to within 1 part in 100,000. The distribution of matter on scales of hundreds of millions of light-years was broadly uniform, and yet the universe was clearly not perfectly smooth. Galaxies exist. Galaxy clusters exist. The cosmic web of filaments and voids had been mapped across hundreds of millions of light years. Somehow, the smooth early universe had developed structure. Something had to provide the seeds from which structure grew. Perfectly smooth matter does not clump. Gravity needs something to work with. A density slightly higher here, slightly lower there, the kind of unevenness that gravity can then amplify into the structures we see. Where did the seeds come from? The answer is the quantum vacuum. In the early universe, before the formation of atoms, before the first stars, in the first tiny fraction of a second of cosmic time, cosmologists believe the universe underwent a period of extraordinarily rapid expansion. This period, called inflation, stretched the universe by an enormous factor in a very short time. Space itself expanded faster than light travels through it. During this expansion, the quantum vacuum was doing what it always does, fluctuating, virtual particles flickering into being and vanishing, energy rippling through empty space in the restless way the uncertainty principle demands. These fluctuations, at the scales where they occurred, were tiny, quantum ripples, probabilistic, transient. But inflation stretched them. Those density variations are the seeds of every galaxy that exists. As space expanded, these quantum ripples were pulled apart, stretched from subatomic scales to cosmic scales, frozen in place by the rapid expansion before they could oscillate back. The fleeting quantum jitter of the vacuum, which would under normal circumstances vanish before any instrument could catch it, was dragged into the macroscopic world by the expansion of space itself. What had been a quantum fluctuation became a density variation in the distribution of matter, a region slightly denser here, slightly less dense there. We are looking at a photograph of the quantum vacuum. The oldest light in the universe is carrying the imprint of quantum fluctuations that occurred in the first moments of time. The pattern of galaxies in the universe today, the large-scale structure of the cosmos, is the amplified echo of quantum mechanics operating in the very early universe. The largest question, the physicist Edward Tryon had an idea in 1973 that he expressed out loud without quite meaning to, in the middle of someone else's lecture. He blurted it, was laughed at gently, and spent the next months turning it into a paper. The paper was published in Nature in December of that year under the title, "Is the Universe a Vacuum Fluctuation?" It is the right question asked at the right time by someone who had been sitting long enough with the quantum vacuum to see what it implied. Here is the reasoning. Now ask, what is the total energy of the observable universe? We have established that the quantum vacuum is not nothing. It is a structured state, a sea of potential, a ground from which virtual particles can arise. And we have established that those virtual particles are permitted to exist as long as the energy they borrow is repaid within the time the uncertainty principle allows. Larger fluctuations must be briefer. Smaller fluctuations can persist longer. The relationship is exact, written into the mathematics of quantum mechanics with no wiggle room. Now, add in the gravitational potential energy of all that matter, the energy associated with the gravitational field that binds everything together. And here is the key. Gravitational potential energy is negative. Two masses pulled together by gravity represent a lower energy state than the same two masses far apart. Gravity, in the standard accounting, contributes a negative number. Tryon's suggestion was this: what if those two quantities, the enormous positive energy of all the matter and radiation, and the enormous negative energy of the gravitational field, cancel exactly? What if the total energy of the universe is zero? The universe, in this picture, is a fluctuation of the quantum vacuum that happened to some to nothing, a cosmic accident that cost nothing and therefore has lasted 13.8 billion years, and counting. Matter and gravity are two components of the same zero-sum account. The matter creates the gravity, and the gravity balances the matter, and the whole thing adds up to the energy of the vacuum from which it flickered. The cold, far future, there is something almost weightless about this, in both senses. The universe may be literally weightless, zero total energy, a fluctuation that never had to be paid for, and the thought itself has a lightness to it, a kind of relief. Existence does not require justification. It does not have to be purchased from somewhere. It is perhaps free. Everything we have described so far is the universe building itself. Quantum mechanics lighting the stars, uncertainty seeding the galaxies, the vacuum fluctuating into an entire cosmos. But quantum mechanics also has something to say about the universe unmade. The stars will not burn forever. They consume their fuel at rates determined by quantum tunneling. Every proton that crosses its barrier is one less fuel reserve. The sun will burn for roughly 5 billion more years. The smallest, most frugal stars, dim red dwarfs so cool they are barely distinguishable from very large planets, can smolder for trillions of years. But even they will eventually exhaust their hydrogen and go cold. But they do not. What holds them up is called electron degeneracy pressure. And electron degeneracy pressure is quantum mechanics. White dwarfs are particularly interesting from our perspective. They are dense, very dense. The mass of the sun compressed to roughly the size of the Earth. Gravity would like to crush them further. There is nothing burning in their cores to push back. By ordinary physics, they should collapse. Here is what that means. The electrons inside a white dwarf are packed extremely tightly. Their positions are constrained to a small volume. The uncertainty principle responds to this constraint by demanding that their momenta become large and uncertain. Electrons in a highly compressed system must have a wide distribution of momenta. They must be, in effect, moving very fast. And that motion creates an outward pressure, not the pressure of heat, not the pressure of burning, the pressure of quantum mechanical restlessness, the refusal of confined quantum particles to be still. Here is what that means. The electrons inside a white dwarf are packed extremely tightly. Their positions are constrained to a small volume. The uncertainty principle responds to this constraint by demanding that their momenta become large and uncertain. Electrons in a highly compressed system must have a wide distribution of momenta. They must be, in effect, moving very fast. And that motion creates an outward pressure, not the pressure of heat, not the pressure of burning, the pressure of quantum mechanical restlessness, the refusal of confined quantum particles to be still. This pressure is, as far as the theory tells us, permanent. It does not diminish over time. It does not require any fuel. It is not a fire that burns out. White dwarfs are held up by a pressure that will still be there in 10 trillion years, when the last red dwarf has faded to darkness. The same principle holds a neutron star together at even higher densities, operating on the neutrons themselves. And black holes, surely those are permanent. Surely nothing defeats a black hole. And then there is the longest game, the speculation that even protons may not last forever, that the particles of matter themselves, given enough time, will decay into lighter constituents, very slowly, at rates that make the current age of the universe look like a blink. If proton decay occurs, then in the unimaginable future the matter in white dwarfs and neutron stars will slowly dissolve. The remnants of stars will evaporate. The universe will be left with black holes. The vacuum defeats a black hole. Stephen Hawking showed in 1974 that black holes radiate, that virtual particles produced near the event horizon by the uncertainty principle can be pulled apart by the tidal forces of the black hole, with one member of the pair falling in and the other escaping. The escaping particle carries energy away from the black hole. Over time, the black hole shrinks. It grows hotter as it shrinks. Eventually, it evaporates in a final burst of radiation. The timescales involved are staggering. A black hole the mass of the Sun would take about 2 times 10 to the 67th years to evaporate by Hawking radiation. The current age of the universe is about 14 billion years. The number of current universe lifetimes that would need to pass before a solar mass black hole evaporated is so large it has no useful analogy. But it is finite. Every black hole in the universe has a finite lifespan. The end of the universe will look very much like the beginning of one. What can be carried through a closed door? Schrödinger intended this as a criticism. He was pointing out what seemed to him an absurdity, that the quantum mechanical rules designed for atoms could not, without producing nonsense, be applied to objects at the scale of cats. The quantum world and the ordinary world were, he felt, governed by different rules, and pretending otherwise led to contradictions. Erwin Schrödinger, who gave quantum mechanics its most famous equation, once proposed a thought experiment that has since become perhaps the most discussed image in all of physics. He imagined a cat placed inside a sealed box with a small amount of radioactive material and a mechanism that would release a poison if a single atom of the material decayed. According to quantum mechanics, the atom exists in a superposition of decayed and undecayed states until it is observed. If the atom is in superposition and the cat's fate depends on the atom, then the cat too is in superposition, simultaneously alive and dead, neither one nor the other, until the box is opened and the superposition collapses. Whether he was right about this is still debated, but his thought experiment illuminates something that matters deeply for our question. The quantum mechanical description of the universe is a description of possibilities. The wave function tells you the probabilities. It does not tell you what actually happens. And when you try to apply this description to the universe as a whole, to write down the wave function of everything, you run into the question that Schrödinger's cat makes vivid. Who or what is doing the observing? Who is collapsing the wave function? Inside the box, from the cat's perspective, there is no external observer. The box is closed. There is nothing outside the system to look in and determine which possibility is real. And if you extend this to the universe as a whole, the problem becomes even starker. The universe has no outside. There is no external position from which to observe it. There is no hand reaching in from beyond the cosmos to collapse its wave function into a definite state. In the 1950s, a physicist named Hugh Everett proposed a solution. He suggested that the wave function never collapses. Every possibility described by the quantum mechanical superposition is equally real. They simply occur in branches that cannot interact with each other. The cat is alive in one branch of reality and dead in another. Both branches are equally real. There is no collapse, only branching. Whether Everett was right or wrong, the attempt to apply quantum mechanics to the entire universe reveals something important. The universe behaves quantum mechanically. The density fluctuations that seeded the galaxies were quantum. The tunneling that lights the stars is quantum. If inflation occurred, the mechanism that drove it was quantum. And if the origin of the universe from a vacuum fluctuation is correct, that event was quantum. At every point where we push our understanding to its deepest level, quantum mechanics is the language the universe speaks. Not a language for small things that can safely be set aside when dealing with large things. The language of reality at every scale. At every point where we push our understanding to its deepest level, quantum mechanics is the language the universe speaks. Not a language for small things that can safely be set aside when dealing with large things. The language of reality at every scale. We have come a long way from Helgoland. We have watched Heisenberg find the door in the mathematics of the atom. We have seen that door open onto a universe fundamentally different from the clockwork one that preceded it. We have followed the quantum thread through virtual particles and vacuum energy, and stellar fusion and galactic seeds. We have seen the vacuum produce particles, and the particles produce stars, and the stars produce us. And then we picked up Tryon's extraordinary suggestion that the universe itself might be a fluctuation of the quantum vacuum, a cosmic accident that costs nothing and therefore has no need to end. Let us now be honest about where this leaves us. Tryon's idea is beautiful. It is mathematically consistent with what we know. It connects the universe's origin to the same quantum mechanical processes we observe operating throughout the universe today. But it does not fully answer the question it seems to answer, because the quantum vacuum is not nothing. Return to the empty cup. We established that the supposedly empty interior of an evacuated cup is filled with the quantum vacuum, with virtual particles and fluctuating energy, and the restless activity the uncertainty principle demands. And we have been treating this vacuum as the source from which the universe might have emerged. The quantum vacuum is not nothing. It is the emptiest possible state of a physical system that already exists. It is nothing in the sense of containing no matter or radiation, but it is something in the sense of having laws, structure, fields, rules. The vacuum gives us the universe. But who gave us the vacuum? Every physical theory we have is a description of how things behave given the laws. Classical mechanics tells you how billiard balls move given the laws of mechanics. Quantum mechanics tells you how electrons behave given the laws of quantum mechanics. General relativity tells you how space-time curves given the laws of general relativity. Every theory presupposes the laws it operates within. When you ask where the laws themselves come from, you are asking a question that lies outside the scope of any theory built from those laws. You are asking physics to stand outside itself and explain its own foundations. And physics, being built from those foundations, cannot do this. It would be like asking a language to explain the grammar rules of that language using only sentences in that language. The explanation would already be using what it was trying to explain. The honest position is that none of these answers is complete. None of them have been verified. None of them explain without residue why there is something rather than nothing, why there are laws rather than no laws, why the vacuum that produces universes exists rather than an absolute absence that would produce nothing at all. Some physicists suggest that the laws of physics had to be exactly what they are, that mathematical consistency alone could explain why the laws have the form they do. Others suggest that many different sets of laws exist, each in its own universe, and that we happen to find ourselves in the one whose laws permit our existence. Others suggest that this is a question not for physics, but for mathematics or philosophy, or something we do not yet have a name for. The cup still sitting there, and yet look at what we now know about what you are looking at. It is still on the table. Nothing about it has moved. The ceramic walls are where they were. The inside is where it was. If you reached over and touched it, it would feel exactly the way it has always felt. Smooth, room temperature, solid. The cup exists because atoms exist. Atoms exist because the strong force holds nuclei together, a force whose behavior at nuclear scales is governed by quantum mechanics. The electrons that give the cup its solidity, the degeneracy pressure that makes the atoms impenetrable to each other, arises from the uncertainty principle, the same principle that makes the vacuum restless. The cup was made by human hands, and human hands are made of carbon and oxygen and calcium and iron, elements forged in stellar cores by quantum tunneling and scattered across the galaxy by quantum processes in dying stars. The atoms of the cup have been in various configurations for billions of years. Some of them were in stars. Some of them were in clouds of gas between the stars. Some of them were in the earth before life began. The cup itself is far from any deep source of heat, but the ceramic atoms are vibrating with their thermal energy. Those vibrations are quantum. The specific energies at which atoms can vibrate are discrete, quantized, described by Planck's law, the result that started the entire quantum revolution when Max Planck found it in 1900 while trying to explain the spectrum of light from a heated body. Nothing about the cup, from the structure of its atoms to the light reflecting off its surface to the space inside its walls, is outside the reach of the quantum mechanical framework. And that framework, the one that describes the cup, is the same framework that may describe the origin of the universe. The quantum mechanical process that makes virtual particles flicker inside the cup is the same process, applied at different scales and different energy regimes, that may have flickered the entire universe into being. We have now watched physics make the same attempt and encounter the same failure. Every time we push to the bottom of what exists, we find quantum fields, uncertainty, rules, structure. The universe emerges from the quantum vacuum. The quantum vacuum has laws. The laws emerged from, and here the sentence stops. Not because we ran out of patience, but because we genuinely do not know. Because the tools we have were built for operating within the laws, and this question is about what stands beneath them. We began this journey with a simple request. Try to imagine nothing. You found that you could not. Every attempt produced something. A dark space, a quiet room, a minimal expanse. The mind cannot construct a true nothing because the mind is a something, a process running in time and space, and every picture it draws is drawn on those same foundations. This is not a failure of physics. It is physics being honest about where it currently stands. The locked door is real. The uncertainty about what is on the other side is real, and the honesty required to say, "We do not know," rather than "the question is meaningless," or "we have already answered it," is itself a kind of knowledge. The fact that we are asking the question at all is remarkable. A universe that flickered into being from a quantum vacuum, according to no plan and for no purpose, has produced, in one small corner of itself, creatures who can trace the logic of their own emergence back to the vacuum that produced them. Creatures who can look at the restless activity of empty space and say, "This, perhaps, is where we came from." This uncertain, flickering, law-governed nothing that is not nothing at all. This is not a failure of physics. It is physics being honest about where it currently stands. The locked door is real. The uncertainty about what is on the other side is real. And the honesty required to say, "We do not know," rather than "the question is meaningless," or "we have already answered it," is itself a kind of knowledge. The cup is still on the table. The quantum vacuum is still inside it. The uncertainty principle is still at work. Virtual particles are still flickering in the space between the ceramic walls. The floor is still holding your weight through quantum degeneracy pressure. The star that warmed the day is still burning through quantum tunneling. The atoms of your body, forged in stars by quantum processes, are still arranged in the particular configuration that makes you the thing that is thinking about all of this. Nothing has moved. Everything has changed its meaning. The question of where the laws themselves came from is still open. It may remain open for a very long time. There are theoretical frameworks being developed that might one day address it. A complete quantum theory of gravity, a framework that treats space-time itself as an emergent phenomenon from more fundamental structures, something that does not yet have a name and may require a mathematical language that does not yet exist. We are at the edge of what we know. Not in a comfortable way, not in the way of having almost finished the job, but in the genuine way of standing at a precipice beyond which the path has not been built. It is waiting, the way the deepest questions always wait. And in the waiting, in the honest acknowledgement of where the path ends, there is something closer to wisdom than any premature answer could be. Rest with it. The door is still there. The wondering goes on. You have been watching the entire history of the universe. Do not forget to like and subscribe and leave a comment telling us what you think. Thanks for watching, and we will see you next time.